Welcome everyone. In this video, I will be covering section 14.6, which is on directional derivative and the gradient vector. Now remember the meaning of partial derivative from the earlier sections. The first partial derivative of a function of two variables tells us the slope of the tangent line at a given point, either in the x direction or the y direction. F sub x, a partial derivative of f with respect to x, is the slope of the tangent line in the direction of the x-axis, and f sub y, which is the partial derivative of f with respect to y, is the slope of the tangent line in the direction of the y-axis. So when you do partial derivative with respect to x, you have to keep y as a constant. By that, what we mean is you are taking the intersection of the surface with the plane y equal to constant, which is a vertical plane. Then they meet at a curve, and then you're going to take the slope of the tangent line in the direction of the x-axis. So that is f sub x, or partial derivative of f with respect to x. Same thing with partial derivative of f with respect to y. So you take x as a constant, which means x equal to constant is a vertical plane, and you take the intersection of the surface with this vertical plane, and they meet at a curve. Then you take the slope of the tangent line at a particular point on that curve in the direction of the y-axis. That is f sub y. So f sub x, a partial derivative of f with respect to x, gives the slope of the tangent line to a surface in the positive direction. F sub y xy, which is the partial derivative of f with respect to y, gives the slope of the tangent line to a surface in the positive y direction. A directional derivative of f gives the slope of the tangent line to a surface in any direction. That is known as directional derivative. So let's see how it is defined. Write an expression as a limit for the directional derivative of f at the point x0, y0 in the direction of a unit vector u with components a comma b. Unit vector, which means a vector of unit length, vector of length 1. How do you interpret it as a rate? How do you interpret the directional derivative as a rate? How you interpret it geometrically? So the directional derivative of f at x0, y0 in the direction of u, keep in mind u has components a and b. Then we write directional derivative as du of f at x0, y0, which is limit as h approaching 0, f of x0 plus ha, y0 plus hb minus f of x0, y0 divided by h. Here a and b are the components of the unit vector u, or the directions of the unit vector u. If this limit exists, so when we gave this definition, limit definition for partial derivative of f with respect to x or partial derivative of f with respect to y, we only had an increment for one of the two, because when we take fx, we keep y as a constant. When we take fy, we keep x as a constant. So here we are incrementing both x0 and y0. We can interpret it as the rate of change of f with respect to the distance at x0, y0 in the direction of the unit vector u. Geometrically, if P is any point x0, y0, or the x and y coordinates, and z is given by f of z0 is f of x0, y0. The reason is z is the surface given, which has the equation f of xy. So when you plug in x0, y0 for x and y, what you get is z0. Geometrically, if P is any point x0, y0 and f of x0, y0 on the graph of F, and C is the curve of intersection of the graph of F with the vertical plane that passes through the point in the direction of U, then d sub u f of x0, y0 is the slope of the tangent line to C at P. Similar idea like f of x and f of y, because there it is the slope of the tangent line in the direction of x-axis or y-axis. Here it is in the direction of the vector u, unit vector u. That's the only difference. So if you look at this picture, we have a surface which is kind of downward paraboloid to just by looking at it, we are able to say that it's kind of downward paraboloid kind of a surface, but it could be any surface. And then we have that unit vector in this direction, which is in pink, in this direction, that is a unit vector. And then we have unit vector has the components A and B along the x direction and the y direction. They are the components A and B. And you imagine you are raising a wall, you are having a plane through that vector U and also passing through the point P, x0, y0, z0. So you have a plane passing through the vector u, which intersects the given surface along a curve. Actually, the intersection is this plane, and the slice is kind of similar to the slice that you see behind on the surface. So it intersects along a curve, and this curve, and you are taking the tangent line at the point P, which has coordinates x0, y0, z0. Then as you increase your direction along U, if you walk along U, if the slope of the tangent line, whatever the slope of the tangent line is, here in this picture, it looks like negative. It could be positive or negative or anything. So if the slope of the tangent line to this curve at the point P x0, y0 is known as a directional derivative in the direction of U. If f is differentiable, write an expression for du of f at x0, y0, directional derivative in the direction of u, f of x0, y0, in terms of partial derivative of f with respect to x and partial derivative of f with respect to y. So we can write that as du of f of x0, y0. So partial derivative of f with respect to x at the point x0, y0, a, plus partial derivative of f with respect to y at the point x0, y0, b. So what are a and b? A and b are the components of the unit vector u, unit vector which is of length 1. So in this definition of directional derivative, if you replace this u vector by I vector has got components 1 and 0. So this will be A, this will be B in the formula. So it becomes fx xy times 1 plus fy times 0. So it is just fx. The partial derivative, directional derivative of f in the direction of I, instead of u, if you replace that by I, that will agree with the partial derivative with respect to x definition. Same way, if you take u equal to j, which has component 0 and 1, because j is a standard basis vector in the direction of y, so x coordinate is 0, 0, 1, then dj of f So here in this component, a equal to 0, then b will be equal to 1 if it was j, if u was equal to j. Then um, the first expression will become 0, second expression will exist. So dj of f equal to f sub y. In other words, the partial derivatives of f with respect to x and y are just special cases of the directional derivative. Problem number 4, based on this directional derivative, is done um, in the videos of this section. Please refer to the set of videos for this section. So this is part A of section 14.6, and in the next part, I will be covering the second half of this section 14.6b. These are only concepts for the problems that are there in this handout, including the additional suggested problem. Some problems from the additional suggested problem, you can refer to my videos for this specific section. Hope this video helps.